Yes, hi and welcome everyone to this 1W Minds seminar. Today's speaker is Yingzhen Li. She's a senior lecturer at Imperial College London and also a Turing Fellow at the Alan Turing Institute. She obtained her PhD in 2018 from the University of Cambridge, and before joining Imperial College, she has also worked at Microsoft Research. Her research concerns, among other things, probabilistic graphical model design, uncertainty quantification, inference and computation techniques, as well as robust and adaptive machine learning system. Today, she's going to speak about the identifiability of switching dynamical systems. So the floor is yours.
Okay, so thank you for the introduction and thank you for the invitation. So yeah, today I'm going to say a bit about basically what we've been doing for the last few years regarding a deep generative model on sequence data, and in particular, we are interested in this kind of switching behavior within a time series sequence, and we are trying to figure out exactly what kind of guarantees or what kind of representation learning properties that we can talk about deep generative models apply to this dynamic data that has this kind of switching dynamic behavior. Okay. So maybe let me first motivate why this is interesting. Okay. So essentially my journey on working on deep generative models for sequence data starts from 2018. Well, when I was still a PhD student and did an internship at Disney Research. Okay, so at the time, we are interested in video generation. So you need to bear with me that this is now 7 years ago. So we should appreciate basically how generative AI progressed in 7 years. Okay, very short time. But at that time, right? So we are interested in video generation, but not only just generating some random videos, but instead we want to achieve something called controllable video generation. In the sense that, for example, in this case, I have this training data of these characters, cartoon characters acting at different actions, and I'd like to train a generative model that can control both, let's say, the appearance or the outfit of the character as well as the action of the character. So one thing to say here is that this is done in a purely unsupervised way, which basically says that my training data just looks like this. There is no label about, okay, so which character is in this video and what kind of action it is doing, but we just want to make sure that it's trained in a pure unsupervised learning way, and then we can generate things that looks like this. Okay, so I mean, this works, otherwise I cannot publish this paper. How does it work? Well, if you know how generative modeling works, usually you build a graphical model and then parameterize it with neural networks and then train it with whatever interesting methods like variation autoencoder. So in our case, we are also doing the same, except that we have some structure design for this graphical model. You can basically see that in this case, you can think about the X as the video frames. We assume that there are two groups of latent variables that leads to this generation of the videos. So the F variable represents some kind of global content that is invariant through time. For example, in this case, that would be the content or the outfit of the character. The Z1 to ZT variables that basically attach to each of the frames represent the dynamic variables, the latent dynamic variables on the sequence. So in this case, that would be the action sequence of the character. Okay. So the recipe for the neural network was quite standard at that time. Transformers was not that mainstream, so we still used LSTMs to parameterize these probability distributions and also use the CNNs to help us generate the video frames. The training method, as I said, is pretty standard in probabilistic graphical models and deep generative models. And in this case, we just do the variational autoencoder objective, which is the elbow. Okay. So this model empirically works, as I show you in the very first slide, that you can generate this video sequence with these controllable features. However, there is actually no guarantee that this will succeed. Okay, so I just tell you two ways that this model can cheat. Okay, so the first idea is, in LSTMs, if you understand how LSTM work, LSTM also has these deterministic hidden states. Okay, apart from the stochastic hidden state. So this basically means if the LSTM learns to just remember and copy the deterministic hidden state, okay, never forget, then essentially it can just, remember the content information and then just keep copy on. So this basically tells you that these ZT variables, which is supposed to only capture the dynamic information, can also capture the static information, like in this case, the content. Okay. So on the other hand, one thing that I haven't actually told you until now is essentially this video, when we collected the data, the underlying simulation is actually deterministic. So it means that the ground truth dynamical system itself is deterministic. So we know that if we have a deterministic dynamical system, then as long as we know the system equations as well as the initial conditions, then we can simulate the entire trajectory up to some numerical precision. Okay, so this basically says if F captures the initial condition, okay, of the underlying deterministic dynamical system, then this also says that F captures the temporal information, in this case, the movement or the action information of the character sequence. Okay, so I just told you two ways that this neural network can cheat. Basically says that there is no guarantee that these variables are supposed to capture only, let's say, the desirable information as designed. I mean, so in practice, right, this might not happen because you can apply basically, engineering tricks, and this is basically what I did. I did a very hard code engineering, doing all these kind of deep learning algorithmic tricks. Okay, so I think at the moment, given this progress in Gen AI and language models and image generation models, we need to really appreciate that engineering is key to lead to the current success. Okay. However, if you just based on the engineering success and then tell people that, okay, I give you a generative model with some graphical architecture, I will tell you this variable captures this information, other variable capture this information, you probably shouldn't believe in me that early, saying that, okay, so this is just empirical result, there is no theoretical guarantee. Okay. So maybe let's just go a little bit deeper to see where does this, problem really come from. Okay, so let's step back a little bit, going from video to just image generation. So technically speaking, most of the generators that you have now in the market can more or less be represented in this way, that you have some initial noise, let's say something from Gaussian distribution, and then you transform the Gaussian noise via a very powerful neural network that will basically give you the final generation results, which is, let's say, an image of a tomcat. Okay, now imagine you can do also the following. So you can first rotate the initial Gaussian noise, okay, which results in another noise, but the distribution speaking is also from a Gaussian distribution. And then you can actually construct another neural network, which first revert the rotation and then copy the previous generator G. Okay, right? So you can now basically see that in this case, the resulting image is still the same. And in fact, it will return basically the same generation result as the original generator every single time. Okay, so this is essentially the problem of non-identifiability. It says that for deep generative models, unless you make suitable assumptions, otherwise, by purely looking at the generated image result and see the quality of that, you cannot tell whether this image comes from, let's say, the generator G or the generator G prime. Okay, so it basically says that if you only care about image quality, then maybe you don't care too much about this problem. But if you also care about what kind of representation, which is basically the latent space Z variables, what kind of representations that you've learned from this generator, then identifiability is something that you need to discuss, because otherwise you cannot differentiate or distinguish between these two generators, so that they might get different representations that you don't actually know. Okay, so I hope this gives you some interesting motivation about why we care about some kind of guarantees in terms of the latent representations from a deep generative model. So maybe let's talk a little bit more about more precisely what we mean by guarantees in terms of this representation. Okay, so it's actually coming from a workflow that is, inspired from causal discovery. Okay, but we just adapt this kind of workflow from causal discovery to deep generative models. And in this case, we call it identifiable deep generative models. Okay, so the first step for this in this workflow is you need to write down basically your model assumptions. In the causal discovery language is called a structured causal model. Okay, for example, you can say your latent variable z comes from some kind of transformation of the random noise, and then your observations, let's say the images, comes from another transformation of your latent variable, maybe plus some noise. Okay, so in deep generative models, right, you use deep neural networks. So basically, it says that these f and g functions are neural networks. Now, think about how you're actually going to train this deep training model, right? So your training data only contains copies of X, i.e. images. So this basically says the Z variables are unobserved. So it means that when you train the models, let's say with maximum likelihood, you need to compute the marginal distribution over X. So now identifiability, which is related to what I discussed before about this representation, basically asks the following question. If I have two models within this class of deep generative models, such that they basically return the same generative result every single time, okay, then can I say anything about whether, let's say, the corresponding neural network functions, these f function and g functions, have some kind of equivalence relationship? Okay, so this is essentially what we are going to talk about in terms of identifiability. We will talk about it in detail later when we go to the actual work. Okay, so once you get this identifiability guarantee, which basically says you have some confidence in terms of, let's say, if your model fits well, then what kind of representation you will get, then you just go on and actually fit your model to the data and then check whether your model fits well. And then afterwards, you use your model to get representations and then answer all these kind of interesting questions related to controllable generation and also related to some other causal questions that you want to ask. Okay. So before I actually tell you about the actual work related to this dynamic modeling, okay, so I want to say something about the caveats first, okay? So identifiability proofs is not learning guarantees or estimation guarantees, okay? It actually makes very strong assumptions. So it assumes there's no model error, okay? It assumes you need to use consistency estimators for learning, for example, like maximum likelihood estimation. And you also need to assume that you can get to the global optimum given, let's say, the infinite amount of training data. Okay, so these all look very unrealistic. Okay, but why should you still care, right? So I mean, identifiability is actually a fundamental concept of a statistical inference. So I hope that I don't need to convince a statistician for that. Okay, but for deep learning people, maybe one thing I would say here is that, okay, so identifiability is fundamentally about, okay, if you make some kind of, say, neural network architecture assumptions to your model, and then you're hoping that, okay, this layer of your neural network will get this kind of representation, another layer of your neural network will get some other kind of representation, then identifiability is the very first step that you need to show in your sort of like theoretical proof about your claim in terms of the representation learning guarantees. Okay, in other words, should I actually trust my discovery results when my deep generative model fit the data? So this is the very first step to answer this question. On the other hand, if you even though if you don't care about exactly what kind of representations that you've got, right? The one thing I will also argue here is that nowadays, given you have a very big deep neural networks, you can think about them as ways to compress knowledge from real world data to a big neural network model. Okay. However, being able to store knowledge or compress knowledge is not necessarily the same as being able to use the stored knowledge efficiently. Right? So think about basically, file systems in your laptop, right? So you know that your kind of like the documents are stored in the file system, but the file system is organized in some way so that when you actually want to open up your document again, it actually use that file system to retrieve information. So this is actually why structure will actually be helpful. In other words, structural representation will actually make a downstream use of the features much easier. Okay, so hopefully I've given you quite some motivations. So I'm going to actually talk about the the real world. Okay, so this is the work that we published last year at ICML 2024. So this work is led by my PhD student Carlos and also in collaboration with Yixing Wang from University of Michigan. So going back to basically the video generation problem, right? So one thing that we know that why video generation is so difficult is that basically the underlying dynamic model of a video sequence can be very, very complicated and non-stationary. Okay, so in general, there are a lot of different ways that a time series sequence can be non-stationary. So there is no one model that fits in all, so we need to make some assumptions. So in particular, in this case, we made this following assumption about regime switching behavior in time series data. So if you think about basically a video of, let's say, salsa dancing, right, then you notice that they have actually different patterns or different regimes in terms of their dancing patterns, like, spinning right now, and, yeah, this is spinning, and then there is this moving forward and backward, right? So these are basically just different regimes or different switching states of the time series behavior. Okay, so we assume basically within the same regime, the behavior of the time series is stationary. Okay, so this does not say the sequence cannot be non-stationary because the regime switching pattern itself can be non-stationary. Okay, so yeah, within the same regime, the dynamics can be stationary. The causal dependencies might be sustained across time steps and etc. Okay, so this basically leads to our model design. So we are going to start from the simpler case, which is something called Markov Switching Models. Okay, so in this case, I mean, it is also called auto-regressive HMM, hidden Markov model, if some of you actually know this. So in this case, you have these X observations. Okay, think about it as sort of like the key point tracking results in your video by tracking basically the dancer's movement. So the latent variable S, they are discrete. Okay, and we assume a conditional first order Markov model, which basically means that condition on your state, the transition distribution of your observation X sequence is first order Markov. Okay, and also we assume this is conditionally stationary. So now the interesting question here is that can I say anything about, let's say, identifiability, right? And remember previously from the very first example that if I just give you this figure and then tell you about identifiability, then you shouldn't believe me. You should actually ask me about what are the assumptions that you're going to put on this, parameterization of the arrows. Okay, so this is what we are going to do next. So our basically one of the major results in this ICML paper says the following about identifiability. So it says this Markov switching model is identifiable up to state permutation when you have these two conditions satisfied. So first, state permutation is something that you need to accept. For example, if you think about Gaussian mixture models, right, you can identify the components, but you cannot identify the labels of the components because they can just like do permutation. So yeah. So the two conditions, the unique indexing, just think about it as we are not using two different integers to index the same dancing pattern. So this is what unique indexing is saying. So another condition here is about how we are going to parameterize this transition distribution because we are going to use neural networks. Okay, so we assume that, okay, we are going to use Gaussian distribution to parameterize the first conditional first order transition distribution with the mean function and variance function depending on the previous observation and the current state. Now, we just want this mean function and the covariance function to be infinitely smooth respect to the previous observation xt minus 1. So this basically says, if you're going to use neural network to do this, then the architecture itself is less a problem, but the kind of activation function that you're going to use would be very important. So it says you need to use these smooth activation functions like sigmoid and soft plus. So ReLU is problematic here because ReLU is not smooth around this origin point. So let me give you some intuition why this proof, this result require these assumptions. So, think about switching patterns as trying to detect discrete or discontinuous changes in your time series. Okay, so it basically says that your time series itself is non-smooth that contains these abrupt changes. Now, given that we have this mixture model, there are two ways that you can represent these discrete or discontinuous changes. One is basically the switch of your discrete states, this is what we actually want. Another way is to say, okay, my conditional transition distribution on X is also very non-smooth in the sense that the mean function of a Gaussian itself can also be discontinuous. If you allow this second case to happen, then it basically means whenever you see a discontinuity in your sequence, then there is no way for you to tell very sure that, okay, whether this discontinuity comes from a switch of your states, or it comes from basically, a particular state's transition distribution has non-smooth jumps. Okay, we want to avoid this case so that we just eliminate these possibilities and make sure that all the discrete changes are attributed to the switches in the states. Okay, another thing that people might be interested is okay, so why infinitely smooth function rather than just some kind of a smooth function, right? So this is actually related to the actual proof that requires some kind of measure theoretic condition. But the nice thing about analytic function is basically two analytic functions can only intersect at zero measure number of points if they are different. So it basically means that if, let's say, in an interval of X, that these two functions are the same, then they must be the same in the entire space. So this is actually very helpful for our proofs. Okay, so maybe let's go through the proof a little bit and just give you a high level idea. Okay, so the way we are going to prove this result is not by some other previous techniques, but instead we go to the very beginning of mixture models. So one thing to notice here is that the dynamic model for the latent discrete states S here has no dependence on the observation sequence X. So which basically says the latent states dynamics, they are autonomous. So in other words, you can actually write this Markov switching model as a finite mixture model, but it's not a mixture over just a single Gaussian component, but it is a mixture over the entire path. Okay, so now we can actually start to use these identifiability results, classical results in the statistics about finite mixture models. So first, finite mixture models identifiability requires linear independence of the distribution family for these conditionals. So what I meant by linear independence, it basically says that a class of functions that are linear independent if and only if it contains linearly independent functions, like the combination of the function equals to 0, which means that the coefficient needs to be 0. Okay, so this is what we're going to do. So now notice that we have made assumption about this first order conditional Markov transition, okay, which help us to break down this big conditional distribution even further. So this basically says what we can do is to show linear independence for the first two time steps, and then we can prove the later time steps by induction. So now we are going to actually work on the first two signs, and this is basically the heavy lifting part of the proof. And as I said, we need to show that the distribution family is linearly independent. So we're just trying to work out the conditions for the conditional transition distribution, so that the product of two conditional distributions are linearly independent. Okay, so this gives us certain kind of linear independence and continuity equations. Okay. So at the end of the day, we need to use neural networks, which basically says we need to parameterize the conditional transitions. So we use a Gaussian distribution to do that, and then we try to see, okay, what kind of assumption we need to do for these mean and covariance functions to satisfy conditions we identify in the third step. So at the end of the day, this basically just tells you some kind of smoothness conditions for the mean and covariance functions. Okay, so there are some indications about the proof strategy. So the first thing that we should say here is actually this is a major result beyond the hidden Markov model identifiability result, which is like 16 years ago already. Okay, so hidden Markov model you can think about is basically the same as this, except that you remove these edges. So the main problem, or maybe let's say the magical step that we have comparing to the previous HMM result is essentially because when you add in these arrows, then when you make this product of conditional distributions, you can basically see that xt now appears both as the random variable argument in one distribution, but also as the conditional argument in another distribution. So this part actually makes the proof of a linear independence very difficult. Okay, so the other thing that would be very interesting to talk about here is because we use this finite mixture model view of the switching dynamical systems, then the proof actually makes no assumption about the joint distribution for the discrete state path. Okay, and the finite mixture model identifiability result can actually also identify the joint distribution for these discrete states. So it basically says, okay, you can put any kind of dynamic model for your discrete state. Okay, so this basically says if you use a non-stationary transition model for your latent states S, or you use a higher order or even auto-regressive dynamic model for your latent states, then your actual model, basically the marginal distribution over your X, can also be non-stationary and high order Markov. So essentially, it just says that, okay, this model class is actually quite flexible in practice. So the last thing here is, so in certain problems like control and reinforcement learning, people will also have some kind of say action sequence or control signals U as the external input. So if you also want to use this kind of external control signal as inputs, then you can also construct a switching dynamical model in a similar way as we talked about before, and the theoretical result also extend to this case of observing control signals. So maybe before we actually go to see some examples, then I should also talk about how we apply this to a video sequence, right? So we have some nice results about the Markov switching models, but they are still impractical for video sequences because if you directly apply it to video sequences, then your X is basically just a collection of pixels for in each of the frames. Okay. In practice, we are not interested in understanding the dynamics of each of the pixels. Okay. Instead, we are interested in actually understanding, for example, like how these two dancers, well, basically the object in the video, interact with each other. Okay. So this basically leads to what we are actually doing in the video setting. So we are going to lift the previous Markov switching model to latent space. So now in this deep generative model, we actually have a hierarchy of two different sets of latent variables. Now you can think about X here is really the frames in the video, which means pixel values. But then think about these Z variables as sort of like the object representation of the video. For example, again, like this tracking the joint of the dancer, and the S are actually just these labels of the regimes. Okay. So we use this model in our experiment, but again, before that, we need to ask the question about identifiability. So so we basically ask again the identifiability results. Then we do have this theorem. It says as long as your latent dynamic model, basically the MSM part, follows the previous assumption, and the decoder you use to transform the Z variables to your frames satisfy this continuity and injective assumption, then you can have identifiability of this model up to state permutation and affine transformation of the Z latent state. Okay, so this basically says, apart from using, let's say, these smooth activation functions for your transition network in Z, you also need to think about how to parameterize your decoder here, and it actually allows you to use certain kind of leaky radio networks. It's not all kind of radio networks. So the proof is actually not mainly done by us. We basically just use a previous result from this nearest paper. If you're interested, you should check it out. So the idea is the following. So the previous nearest paper talk about identifiability of a generative model when you use basically mixture distribution as your prior on Z. It says if you have a mixture prior on Z on these Z variables, which is identifiable, then as long as you fulfill basically the previous conditions, let's say the injectiveness and continuity for your transformation F, then you can have identifiability results. Now, in the sequence modeling case, right? So our previous result is essentially proving identifiability for the latent Markov switching model prior using this finite mixture modeling result. So this basically means, again, we can group all the variables together and view it as basically a giant generative model that transforms latent sequence into video sequence. And the latent sequence has this identifiable mixture prior. So the identifiability result directly applies to this case. Okay, so let's now actually see some examples. Okay, so switching dynamic systems, they are actually quite useful in practice to do say sequence segmentation. In this case, we basically just train our just previously total model with these neural network parameterized arrows, and also train with variational autoencoder objective. So this is the data set that is simulated from this motion capture data set. So and this is basically just also the one of the person dancing in this salsa. Okay, you can basically see that the result here shows the model has learned to segment the sequence with sort of like different patterns, like spinning and moving forward and backward. Okay, so this is one example. So this is semi-synthetic video. And another case that we've tested about is basically this hip hop dancing. So this is a data set for AISD dance data set coming from UC Berkeley. Okay, so again, so this is a real world video, but there is no ground truth because the database providers, they don't do the labeling. So we can only just look at the segmentation results to see what's happening. I would say first, basically, this model, the reconstruction result is okay, not state of art. We believe that we can make engineering better to make a reconstruction better. But at the end of the day, you can basically see there are some kind of a segmentation result showing certain signal. And in this case, we are guessing that the model has figured out basically the dancer is performing differently when they basically move backward and forward to different positions on the stage. Okay, so that's basically what we did at last year at ICML 2014. So obviously, we are currently working on more sort of like sophisticated dynamical modeling in terms of this switching dynamical behavior. So the first thing that we've been looking at is basically like, okay, so the conditional transition that we looked at previously was only first order Markov. Can we actually also go for higher order Markov transitions? And in this case, that will actually be more related to science data like this brain signal data of neuroscience, and also this climate data. We also look at the other cases where the latent state dynamics is no longer autonomous. So which basically says your previous position of, let's say, the dancer would actually also impact on, let's say, the switching behavior of the state. So this is actually quite common observed in actually, let's say, reinforcement learning problems, especially model-based reinforcement learning. So yeah, we are working on both methods, and one of the approach is already published at a workshop, and another is under submission at the moment. Okay, so another thing that we can also actually discuss is basically about, where there might be some other assumptions that we can also make about this emission function f, so that we don't rely on this injectivity assumption that is probably too strong. Okay, so maybe before I close, I will basically talk about what is still missing at the moment in terms of research. So this is just to show you again the workflow for this causal discovery or based on identifiable deep generative model. So we've already demonstrated to you how the first two steps can be done, especially in this non-stationary time series setting. Now, the interesting thing here is actually you've got very nice theoretical results. How can you bring it to practice, right? So you need to fit your model to the actual data set and then check, whether your model actually performs well. Okay, so this is actually one of the biggest questions right now, I believe, in this field of causal representation learning with deep generative models. So one of the interesting things that we should notice here is whether these kind of deep generative models with identifiable guarantees is they are actually used in practice for production. The answer is actually no. Okay, so if you think about basically the current video generation model available in the market, for example, like OpenAI Sora model and all the other companies' model, right? So how it works is basically based on this non-causal transformer architecture. You first transform the video frames using this visual encoder into some latent representation. But then this latent representation, you are going to basically split it into this kind of space-time patches. Okay, so this basically says it is possible that the future information of the video is used to help you predict the current video frame details. Okay, so this is clearly non-causal because in time series, causality basically means you cannot violate the arrow of time, which goes from the history to the future. So this prediction is made in a non-causal way. So now actually it brings to this interesting question, right? So given that there is actually quite a gap between what we are doing to make this time series generative model identifiable versus the actual video generation model that currently the companies are producing. So the interesting question here is whether, let's say, these end-to-end causal deep generative models are ever possible. Okay, so my personal opinion is the following. So if you think about video sequence again, right? Again, we are not interested in understanding the causal relationship between pixels. Instead, we are interested in basically objects, right? So objects are not obvious to the models purely by looking at pixels, which basically says you need to first get some low-level representations from these perception models like deep neural networks. Okay, so but once you've got some useful low-level representations from these deep learning models, then we can actually start to think about structured generative models that have kind of guarantees in terms of representation learning. Right. Okay, because now you can actually start to talk about the interactions and the desirable causal relationship between the object representations that you've got from your low-level features. Okay. So at the end of the day, what I would say here is what is actually the right balance between, let's say, theoretical research in deep learning models and also the practical kind of development for, say, these real realistic video generation models. I will actually advocate for these things. I would call it scientific alchemy. Okay, so basically at least myself, as a researcher in this statistical machine learning, we would need to figure out basically the theoretical limits to what kind of assumptions are really needed if you want certain kind of a result. But then we should not just stop there and say, okay, so if I cannot get that kind of guarantees, then I just stop. So I will basically say that, okay, so leave the rest to perception, well, deep learning models, and hopefully they will help us to figure out the representations in a good way, on average, you might not have worst case guarantee, but the average case, if it is good, then it is useful for product. Okay, so thank you very much. So I hope this is interesting and not too sort of like difficult to understand. But if you are interested in this paper, then you can scan the QR code. And I will also thank my collaborators, including my PhD student colleagues during basically this entire journey of working on switching dynamical systems.
Thank you very much. I'll start with a question right away. So I was intrigued by this assumption that the mean and covariance functions should be analytical.
Yeah.
So the intuition was that you needed to kind of get equality from dense samples, right?
Yes, indeed. So
Yes.
that is the right intuition, because technically speaking, right? So you're going to basically train your models using samples from your data distribution. So what we are trying to do here is we are trying to say, okay, with probability 0, okay, you will see, you will identify two different functions that have the same behavior, okay? Otherwise, if you don't do these analytic things and allow sort of like these functions to overlap or sort of like be equal in a non-zero measure set, then it means that in practice there is a non-zero probability that you will actually train your model and get two different models that can explain the same data. So this is where, you know, why we want to use analytic functions instead of just some simple smoothness.
Yes. So and my question is basically, so I don't even know if this makes sense, but what happens if we assume that the functions has some certain structure? I don't know, that it's a low dimensional polynomial, or even that it comes from a neural network of a certain structure. Could we do something different then?
I mean, okay, so actually analytic functions, you can think about it as basically just polynomials, right? So because analytic functions, by definition, they are basically infinitely differentiable, which basically says you can actually do this Taylor expansion, okay? So polynomials are definitely satisfying this condition. So now for neural networks, right? So we don't actually know what exactly the neural network function forms are, but we just want to check whether they are sort of like infinitely differentiable. And if you think about it, then for example, if you're using fully feed-forward neural network, then whether the neural network function is infinitely differentiable depends solely on the activation function you use. So that's basically why we said you use smooth activation functions that are infinitely differentiable, like a sigmoid and soft plus.
Yes. So yes. So what I was rather thinking about. So if we assume, so I don't even know if this is sensible, but if we assume, for instance, that M is a low degree polynomial, we would be able to identify it using fewer samples.
Okay, so I guess you are talking about basically this estimation guarantees. So
Mm.
I don't know, to be honest, because identifiability proofs is nothing about estimation, right? So we don't actually have this sort of like asymptotic behavior about how, for example, like how things are how fast the estimation goes to the actual answer. Okay, so that's the thing that we don't know. But one thing that we notice here is that it really depends on your underlying model. Okay, and also in terms of how non-stationary your underlying data is. Okay, so if you actually have a underlying data set that is sort of like a non-stationary but not too non-stationary, then actually having some kind of long sequence with a few samples can actually make estimation work very, very fast. Okay, but yeah, we don't know yet.
Thank you. Are there other questions from the audience? If not,
I
then yes, go ahead.
I want to ask this question about unique indexing,
Yes.
if you don't mind. I'm trying to, okay, so I don't, not sure if I fully understand it, but I'm still going to ask you maybe based on example of this Gaussian mixture models that you mentioned. Is it similar to saying like you sort of know beforehand, let's say given Gaussian mixture model, like how many Gaussians a mixture of, like you know exactly this number. Is it something like this sort of assumption?
Not necessarily. Okay, so here's the idea. So
Yeah.
finite mixtures identifiability results do
Yeah.
not require you to know ahead how many components you have. However, unit indexing basically says you cannot have two overlapping components. So in other words, if you think about Gaussian mixture model, right? So let's say
Yeah.
if you actually have, let's say, four bumps, okay, you will
Yes.
not you will actually think about, okay, four bumps means four components. However,
Yes.
there is a way to actually say, okay, I can have four bumps, but five components where, let's say, the first and the second component are actually the same components. Okay, right?
It's a bit weaker. Okay.
Yeah, so this is essentially basically, if you say unit indexing is not the assumption, then this kind of say four bumps, but with two overlapping bumps, things can happen. So this is the thing we want to avoid. So we basically just intuit here saying that, okay, if you have four bumps of Gaussian modes, then you can only have four components.
Sorry, say that again. I didn't, so can you say the last line again?
So
If
it
four
basically
components
says,
and then
it basically says if your underlying data, underlying distribution only
yeah.
has four bumps of Gaussians, then you only allowed to have four components.
Yes.
This is just what unit indexing says. It does
Yeah.
not say, oh, I need to know a priori, I have four bumps. You can actually say that, okay, a priori, I might know that it has five bumps, then I only use five components.
Yeah. Okay. 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 All right. Thanks. Thanks.
Great. Then I think we thank the speaker once again for a great talk. And yes,